Hi there! I made a small Commodore 64 demo called Quondam Tunneling, featuring a full-screen 3D tunnel effect. You can watch the demo on YouTube, there's a link in the video description. Quondam, of course, is just a quondam word for old school. So this is an old school tunnel effect, and you may have come across similar tunnels on the Amiga, but here it is on the Commodore 64. And in this video I'm going to explain how it works under the hood. The explanation is divided into two parts. First, I'm going to show you that this kind of 3D tunnel is much less complicated than it first appears. There's a trick to it, and when I reveal the trick you'll see just how deviously simple it is. And then, in part 2, I'm going to explain why this conceptually simple effect is nevertheless hard to pull off on a Commodore 64. As far as I know, it hasn't been done before. So buckle up for a journey from hard to surprisingly easy and back to hard again. When you find yourself racing down a tunnel in a demo or game on a modern computer, it's reasonable to assume that there's a lot of calculation going on. For every new video frame, the colors of millions of pixels are recomputed based on some mathematical model of a camera inside a tunnel. But on older computers, this is not possible, and it's easy to see why. In this display mode, there are in total about 30,000 pixels on the screen that would have to be updated on each video frame. But on the 1 MHz Commodore 64, there are less than 20,000 clock cycles per frame. So there's not even enough time to store all the new pixel values into memory, let alone calculate them. For small objects, yes, you can do real-time 3D calculations on a C64, but not for the entire screen. So there must be something fundamentally different going on here. And there is. You are in fact looking at an optical illusion. To explain this illusion, I made a model of a tunnel, and I'm going to place the camera at the opening of the tunnel so we can have a look around. As you can see, there's a black triangle corresponding to the far end of the tunnel, with 3 spokes going outwards. If I turn the camera to the right, the triangle and the spokes move in the opposite direction, and we see more of the right wall. Let's look the other way. To be clear, I'm not moving the camera from side to side here, I'm just turning it to look in different directions. Point being that it's hard to tell the difference. So when you see a figure like this, your brain may conclude that you're looking at a flat picture or that you're located inside a 3-dimensional tunnel. If the figure starts to move, you'll either see the flat picture moving from side to side or get a sensation of turning your head inside the tunnel. We can make it more likely that the brain chooses the 3D interpretation by adding depth cues. At this point, I still see a flat picture moving from side to side, but if we also animate the figure, the illusion suddenly becomes very compelling, at least to my brain. It looks like there's more going on than just flat sideways movement. If your experience is different, please share it in the comments. I'd love to know if this optical illusion works the same for everyone. Now, as we saw, it doesn't work with a static picture. We have to animate the tunnel. So it seems that we still have to perform some computation. But here's the kicker. Because we're actually always looking in the same direction, that animation can be pre-rendered, perhaps on a more powerful computer. And when the tunnel walls have a simple repeating pattern, the pre-rendered animation can be very short. In this case, it's just 4 frames. So what looks like a bunch of complicated 3D vector calculations actually boils down to just showing a rectangular cutout from this 4-frame animation, which is obviously much easier to implement, except that it isn't on the Commodore 64. You may already have surmised that the UFO is rendered with sprite graphics, and so is the scroll text in the upper border. These details support the illusion by tricking you to move your eyes across the screen contrary to the tunnel movements. So they have a surreptitious purpose, but from a technical point of view they're not that interesting, so let's turn them off. I mentioned that this kind of tunnel effect was popular on the Amiga, and there's a good reason for that. You can simply tell the Amiga hardware to start reading pixels from an arbitrary memory address, and then at the end of each line to skip ahead a certain number of bytes before proceeding with the next line. That makes it very easy to display a cutout from a larger picture in memory, which is exactly what we need for this effect, which is sometimes called a Stardust tunnel, after the Amiga game Stardust. The makers of this game also used another trick. Notice how their tunnel is symmetrical in the vertical direction. What's below the horizon is a mirror reflection of what's above it. So what they do is, when the raster beam reaches the point of symmetry, the hardware is reconfigured to skip a negative number of bytes after each line, and that makes it read the same graphics data backwards line by line. This trick cuts the memory requirements in half. So that's brilliant use of the Amiga hardware, but unfortunately we can't do the same thing on the C64. The VIC chip is hardwired to proceed forwards through the address space, so we're going to have to store the full animation frames in memory, and that's going to be a challenge. But let me take it from the beginning. The VIC chip in the C64 has two elementary modes of operation. Text mode is what you see on the regular basic screen. There are 40 by 25 characters on the screen, and you can enlarge the border and fine position the text area behind it. There's 1 byte for every location to specify what character to put there. All in all, those bytes form a 1 kilobyte block of memory called the video matrix. Then there's a 2 kilobyte block of memory with the font definition, specifying how each of the 256 possible characters is built up from pixels. Then there's bitmap mode that lets you display full-screen graphics. Instead of a video matrix and a font definition, you've got a whopping 8 kilobyte block of memory with pixel data for the entire screen. These blocks have to be aligned in memory. Since the entire address space of the C64 is 64 kilobytes, there are 64 possible places where a video matrix can go, 32 places where a font can go, and only 8 places where a bitmap can go. But parts of the address space are unavailable to the VIC chip, so in practice there are 6 locations where you could put a full-screen bitmap. Our tunnel animation only has 4 frames, so could we put them in 4 of those locations? Well, no. Each buffer is large enough to hold a full-screen picture, but remember that our animation frames are larger than the screen. And bitmap mode always starts from the beginning of the buffer. You can't just tell the VIC chip to start reading at an offset or cut out a part of a larger image. So despite the fact that bitmap mode is intended for full-screen graphics, we actually can't use it here because it's too rigid. So we'll have to render the tunnel in text mode, where the screen is built from 1000 characters. Up to 4 colors can be used in multicolor resolution, but there can only be 256 different characters in a font, so we cannot fill the screen with unique characters from a single font. Some characters would normally have to appear more than once. To get around this limitation, we can synchronize the CPU with the raster beam and reconfigure the address of the font definition as we go. This makes it possible to fill the screen with 1000 distinct characters collected from different fonts. Since we have to synchronize with the raster beam anyway, we might as well use a handy VIC trick. By performing certain timed register writes, we can fool the chip into repeating the same row of characters over and over again. So the first 40 bytes of the video matrix are used to pick out 40 characters from a font definition block. Then for the next row of text, the same 40 characters will be taken from a different font, and so on. The benefit of this is that it'll allow us to shift the entire picture sideways by updating just 40 bytes of memory at the start of the video matrix. And I'll show you how that works. The screen is 40 characters wide, but our large animation frames are 64 characters wide. If we arrange the 4 frames next to each other, the total width becomes 256 characters, exactly what you can fit into one font. So the idea is to combine the animation frame number with the current horizontal scroll offset, and that gives us a range of 40 consecutive character codes that pick out a slice of the font. And then for the next row, thanks to the VIC trick, we pick out those exact same characters from the next font bank, and so on throughout the entire screen. The screen is 25 characters tall, but our animation frames are 36 characters tall, so by storing the pixels in 36 different font banks, we can just pick any 25 consecutive ones to complete the cutout. Except there's a slight problem. What I just said is utter nonsense. Because, you see, we can't have 36 different font definitions. A font occupies 2 kilobytes of RAM, that would require 72 kilobytes just for the fonts, and we don't have that kind of memory. It's a 64 kilobyte machine. So obviously I have another trick up my sleeve. How many different colors can you see on the screen? Black, light blue, medium gray, dark gray, and also some dark blue if you look carefully. But some of these colors only appear in a limited area near the vanishing point, and in fact those pixels are rendered with sprite graphics. 4 multicolor sprites to be exact, multiplexed 3 times like so, and moving in perfect sync with the text-based graphics. So let's turn off the sprites to see what remains. I'll also turn down the color saturation, like so. Here we see a full-screen black and white picture, but drawn with the characteristic brick-shaped pixels of the C64 multicolor resolution. Every pixel is made up of 2 bits, so you get 4 colors to choose from, but only half the horizontal resolution. Typically in multicolor mode, each possible bit pair represents an individual color that you configure using palette registers. But if you put the same color twice into the palette, like this, then only the first bit controls what color you see, and the second bit makes no difference. And if you then shuffle the colors, it's now the second bit that controls what color you see, and the first bit makes no difference. In this way, it's possible to store 2 independent pictures in the same memory. And so instead of storing our 36 rows of animation data in 36 font definitions, which would be impossible, we store them in the odd and even multicolor bits of 18 font definitions and use the palette trick to bring out the specific graphics we want. To save clock cycles in the timed code, the deadlines are rather tight, it's best to use an alternating scheme where advancing from one row to the next requires either selecting a new font definition or updating the palette. Each of these operations involves 2 register writes. Then, to make the graphics more varied, and also to throw you off the scent a little, I don't use the exact same color for the bright pixels. I use medium gray and light blue, which are very similar on the C64 and have the exact same luminance, so that the overall contours of the image in terms of dark and light pixels remain the same, but the light pixels have a kind of quasi-random shimmer to them, coming from an unrelated part of the graphics. I could stop here, but I'll throw in a bonus treat for those of you who are as neck-deep into C64 coding as I am. Timing is tight, and we also have to multiplex a sprite carpet in the middle of everything. But it turns out we can get part of the multiplexing for free. This is because the sprites are moving up and down with the background graphics. If we ensure that the font definitions that overlap with the sprite carpet are located in different vic banks, then there's no need to update the sprite pointers, because every line of sprite data is automatically fetched from a different location. And that's how you implement a Stardust tunnel on the C64. I hope you learned something, take care and keep up with the Commodore.